Good morning, guys. I hope you're doing well. Can you guys hear me? If you can't, let me know. Um, if you can, that's great. Um, I hope everybody is doing well. Just a couple of comments about the exam. The exam is Monday. It is during our normal class time. As last time, I will be available in WebEx if anybody has any last minute questions or wants to talk to me about the exam. That is perfectly fine. I will be in WebEx, so you can come and talk to me. It is set as last time with a 2-hour enforced time limit with a 5-minute grace period. There are 7 questions, but some of them are multi-part, so there are 23 blanks that need to get filled in. Again, as last time, I am expecting to see your scratch work, so make sure that your scratch work gets turned into the D2L Dropbox for exam 2. I am not able to give you any partial credit of any kind without scratch work, so I need to make sure that I can see that. Sometimes if you get the answer wrong, you still know what you are doing, so I need to be able to show that I give you credit for that. There is a bonus question, 1 question with 3 parts, so that is available as well. It's not quite as many points as last time, but there are still points available. Are there any questions, comments, problems about the exam before we get started on today's material? Okay. So again, we're going to be talking about gases today. This is not going to be on exam 2. This is exam 3 material. I'm going to give you a little extra time to work with the material for the next exam before we take it. So we're going to be talking about gases today. And that is not what I wanted to do. There. A couple of things that we'll talk about in terms of gases. We'll talk about pressures. We'll talk about a couple of laws that came together: Boyle's law, Charles and Guyot-Sachs law, and Avogadro's law. The guys' names are not important, but I mentioned them. And then we'll talk about the ideal gas law and the behavioral gases that comes with that. And then the last thing we'll talk about is partial pressures, which is also an important part of what we need to discuss. Now, before we get into the new material, let's talk about some old material. So review from what we talked about the last time. Now this is the Vesper summary that I showed you last time. This has actually been posted to D2L. This is available in, if you go to the Vesper, let me show you. Sorry. We go to the Vesper and modeling section. It's under Lab 9 Vesper, and the Vesper table is right there. Again, this is what you'll have on the test, but it is not part of the exam handouts. So that way you can practice with this one. So that is available to you. Move this back out of the way now. So that is the one that we're going to be looking at there. In terms of considering a molecule, let's talk about XeOF2. All right. So XeOF2. If I want to consider XeOF2, I need to consider Xe and O. Those are the 3 contributors to this molecule. I need to know what the number of valence electrons each of those components. Looking at my periodic table. Looking at my periodic table, my Xe is over here. Being over here, he has 2s and 6p electrons for a total of 8 valence. Oxygen, being right here, has the 2s and 4p electrons for a total of 6. And fluorine, being 1 over, has 7. So 6, 7, and 8 for that. And of course, I have more than 9. So 2 of those. 8, 6, 14. That gives me a total of 28 that I need to distribute. Okay, awesome. 28 electrons I need to put around this thing. As always, my Xe goes first because he's written first. I have an O, I have an F, I have an F. It does not matter where I distribute those. It just makes me happy to put them that way. So that's where I put them. I draw 1 bond in between each of those. Okay, that takes up a total of 2, 4, 6 electrons. Take that from there. That leaves me with 22 that I need to distribute. I fill the octets for everything on the outside. So starting with fluorine, he needs 2, 4, 6 to give him a total of 8 electrons around him. Oxygen is the same, 2, 4, 6. And fluorine is 2, 4, 6. 6 times 3 is 18. That leaves me with 4 electrons that need to be distributed. All 4 of those are then placed on my central atom, so on that Xe. So that's my initial structure that I'm looking at. And the next thing I need to do is to determine how happy everybody is with that distribution that I've given it. Well, okay, fine. So we determine that by looking at our formal charge. We do each one individually. I know that Xe brought 8 electrons that are being considered to this. Fluorine brought 7 and oxygen brought 6. And then I need to distribute the electrons to who they go to. So if we want to talk about Xe first, Xe being right here, he definitely has the 1, 2, 3, 4 that are on him as lone pairs. Those belong to him. He also has 1 here from this bond, 1 here from this bond, and 1 here from this bond. That means he has 7, which gives him a formal charge of +1. My fluorines should have 7. They have 2, 4, 6 from the lone pairs, 1 from the bond. That is 7. So all my fluorines are happy. Yay, awesome. My oxygen should have 6, but has 2, 4, 6, 7. So that gives him a -1 charge. Now, I have formal charge, and I have the ability to minimize that formal charge by moving some of those electrons. So that is what I will do. I take one of these pairs of electrons, and instead of it being a lone pair on the oxygen, I move it to a double bond. Okay. That moves me to this structure, where the only thing that has changed is where my electrons are on oxygen. And just because of symmetry, I move them from the top part. Makes my life feel better. So that's where I put that. If we do a reevaluation of this structure and its formal charge, we now see that oxygen should have 6 and has 2, 4, 5, 6. So he's happy. And our xenon, which is Xe, should have 8. He has 2, 4, 6, 7, 8, 2, 6, 7, 8. I can count. Excellent. So that's an 8, and therefore he is also 0. So since I have no formal charge, I have moved my electrons where I need them to be. That's the structure that I need to consider when we talk about our geometry fields. So total electrons on that molecule, again, 28. Okay. What's the electron pair geometry? Well, if I want to determine the electron pair geometry, I need to consider how many pairs are around that central atom. And remember, when we talked about this previously, double bonds, triple bonds are considered one pair. Even though there's more than 2 electrons in it, we consider them as one pair because they exist in the same space. So I have 1, 2, 3 bonding pairs and 2 non-bonding pairs. Okay, so that means that when I come over and look at my geometries over here, I'm looking for 3 bonding pairs and 2 non-bonding pairs, and that is right here. I see ClF3, approximately 90 degrees. My electron geometry is trigonal bipyramidal, and my molecule, the shape that is given to that molecule is T-shaped. So my bond angles are approximately 90 degrees. This one is T-shaped, and this one is trigonal bipyramidal. So that's what I'm looking for there, is that you can assess how many bonding pairs, how many non-bonding pairs, determine what is the electron geometry, and then what is the molecular geometry. And molecular does not include the consideration from these. So it doesn't expressly describe those in it. It is based on that because they have to be there, and that's what gives us our overall structure, but we have a different name because we're only talking about what we can see, the atoms. Okay, so questions about that guy? Okay, awesome. I hope that that was not too bad as far as those. Now, when we talk about gases, the first thing we need to be able to talk about are our units. Units are really important for everything we talk about. So the definition in units of pressure. Pressure is equal to the force per unit area. So it's normally, so our SI unit for that is Pascal. It's 1 Newton per meter squared. Now, if you want details on what that unit is and why it is that, then you can go to your textbook and look at section 5.2. It's not important that we talk about that unless you are interested, and we can, but it really comes down to a measure of how often a gas molecule hits the wall of the container that it's in. So that's a function of how fast that thing is moving, how many of them there are, and how big that container is. Okay. So the units that we use to measure pressure include millimeters of mercury, torr, Pascal, kilopascal, and ATM. Those are all valid units for us to use to be able to do that. One of the other things that we use when we talk about gases is a manometer. That's what we use to measure the pressure of a gas other than the atmosphere. Okay. One of the things that you'll see in the lab, we also, I think it's called the uridometer, and we use that to invert over water so that we can measure the pressure from a separate gas, but we then have to take out the contribution from the water itself. So that is a correction that needs to be done there. One of the other things that we talk about is atmospheric pressure. Now, pressure is exerted by the Earth's atmosphere, okay? So as the molecules in the atmosphere hit things, they exert a pressure on that. That varies depending on our location, okay? It's also dependent on temperature and other weather conditions. So if we have a lot of water in the air, our atmospheric pressure is going to be a lot higher. Standard atmospheric pressure is 1 atmosphere by a barometer. That's the pressure that supports a column of mercury to exactly 760 millimeters high at 0 degrees C at sea level. Okay, that's what we mean by standard atmospheric pressure. Okay, so with 1 ATM. You'll also see that 1 ATM is equal to 670 millimeters of mercury. So mmHg is millimeters of mercury. So that is one of the conversions that we may need to be able to use to do this, right? Questions about our definition? All right. So P is pressure, V is volume, T is temperature, R is our gas constant, and N is the number of moles. Those are the components that we're going to be talking about when we talk about our gas. I'm hoping that I will be able to show you guys this video. Oh no, it's not going to work. Give me 2 seconds. Let me see if I can pull this up here. I forgot I was doing it this way, so give me 2 seconds. So what these are, there's a couple of links that you'll see here. These are places where you can go and look at how do these relationships work. So when we talk about Boyle's law, this is the relationship between pressure and volume. So we can change this volume and then look at what happens to that pressure. So that's what we're talking about. We can move these around and see how it gets different as we move them. You can see that as we come down here, we have a much smaller volume, so we have a much higher pressure. Okay, so that's the idea for looking at those. That gives you the tools to be able to do that. That's our pressure and volume relationship. It is an inverse relationship. Okay, we also have Charles' law. So volume and temperature have a relationship. Okay, that also leads to our pressure and temperature relationship that exists there. We also have Avogadro's law, and that is one where there's a relationship between the volume and the number of moles of gas. So if we have an expandable container, more moles of gas will take up more space. If we don't, then it's going to end up being a higher pressure. Now, we also have temperature here on the Kelvin scale. That's degrees Celsius plus 273.15, just in case you don't remember. So that's what that looks like. Okay. Now, do I need to know what the names of these laws are? Absolutely. I'm not going to say what's Boyle's law and ask you to spit that out for me. what you will find when we look at the material that's available to you on the test, you'll see the ideal gas law, which we'll talk about in just a minute. You'll also see what we call the combined gas law, and that looks like this. So this says P1 V1 over T1 equal times N1 is equal to P2 V2 over T2 N2, where P is pressure, V is volume, T is temperature, N is the number of moles. So if I have a set of conditions and I change those conditions, then I can solve for what is going to happen to one of these things if it's allowed to change. Okay, and that has to happen. Things have to shift because we've made changes. If I change the volume, if I decrease it, then pressure has to increase. And if the pressure doesn't increase, then we have to see changes in temperature. Okay, or we have to have gas that escapes from that. Okay, so we have atoms of that gas that will escape from that if they have any opportunity to do so. Now, this combined gas law is a combination of all three of these versions that we're looking at here. If any of these are constant, like if my volume is constant, then that volume will drop out. And we'll be able to use the equation without the volume in it. Okay, so it is not required that we have all of those things present if they're not all changing. And if only two of these things are changing, then we can use whichever version contains those two things. So if I'm talking about a relationship between pressure and volume, we can look at this one. If I'm looking at a relationship between pressure and temperature, I can look at this one. Okay. And we can use that to do our calculations. And we'll show you what that looks like in just a little bit. And we haven't seen R here, but that is our gas constant. It is also available to you on the exam handouts. It has a couple of different versions depending on what units we're looking at. The one that we typically use when we talk about gases, for reasons that you'll figure out in the laboratory, 0.0821. And that's a 1. Liters times atmospheres over mole times Kelvin. Okay. Anytime we work with gases, this is what we find. This value is what we find when we look at that gas constant. You have an experiment that you're going to be doing in one of the virtual labs where you have to solve for that value. And so, excuse me, you'll need to find the volume, you'll need to find the pressure, you'll need to find the number of moles that you're having, you'll need to find the temperature to be able to solve for that value. Okay, so that's one of the experiments you'll be doing. Awesome. And one of the reasons that we make you do that is because in the virtual lab, it's very difficult to see how complicated it can be to make these measurements. And so we're trying to simulate for you what that would look like if you were actually doing it in a physical laboratory. Okay. So here are some examples that we can talk about when we talk about our pressures and volumes and temperatures and things like that without using our ideal gas. So a balloon is filled with 35 liters of helium in the morning when the temperature is 20 degrees C. By noon, the temperature has risen 45 degrees C. What's the new volume of the balloon? Okay, fine. So I have a volume. This is a volume. I have a temperature. By noon, the temperature has risen, so I have a new temperature, and I want to know what the new volume is. Okay, so that's the one I don't know. If I'm looking for a relationship between volume, sorry, not pressure, volume and temperature, that's V1 over T1 is equal to V2 over T2. Again, do you need to memorize that? No, that is something that you'll be able to see on exam handouts. So you don't need to memorize that. But that is what we're going to be talking about with that particular thing. So my V1 being, and if I want to solve for V2, I'm going to go ahead and solve this for V2. So V2 is going to be equal to V1 over T1 times T2. Okay. Now, my V1 was 35 liters. Okay. My T2 is 45 degrees C, but I need to convert this to Kelvin before I can work with it. So 45 plus 273.5 gives me 318. Ooh. I'm scrolling on that, sorry. 318.15 Kelvin. When we talk about our 20 degrees, that's 273.15 and plus 20. And no, I can't do that in my head. So 293.15 is this temperature here. And so we have our sorry. We have our V1 that's here. We need our T2 to be the one on the top. So 318.15 Kelvin. And the T1 is the one we divide by, so the 293.15 Kelvin. So I can take that 35, I can multiply that by the 318.15 and divide that by the 293.15. And I get, ew, also if I actually do that correctly. Sorry, my decimal was in the wrong place. So times 318.15 divided by 293. And I get 37.9854, yada, yada, yada. I have 3 sig figs in this number right here. So I'm going to report 3 sig figs. And that means that my V2 is 37 point, and actually it rounds to 38.0. Okay. So that's the calculation that I set up there. Again, for me, this becomes, what is it that they've given me? So I label all of the information that they've given me. And then I can figure out which equation I need to use to plug all of this in. Okay? So questions about that? Okay. CaCO3 decomposes at 12,000 C to form CO2 gas and CaO. If 25 liters of CO2 are collected at 12,000 C, what will the volume of this gas be after it cools to 250 C? Okay. So I have 25 liters. This is a volume. I have a temperature. This is my T1. I want to know what's the volume going to be after it cools to my T2. So I'm looking at a relationship between volume and temperature. When we talk about that equation, that's that V1 over T1 is equal to V2 over T2. Okay? If I'm looking for V2, all right, just like we did before, we're going to be using this equation right here. And I'm going to pull this down here so I can do this. All right. We have our V1, which is 25 liters. And that's 5, not an L. Haven't gotten to that yet. Okay. We have our T2 that we're looking at, which is 250 C. So 250 plus the 273.5. It gives me 523.15. And then we have our 1200 plus 273.5. Should be easy. Can't do it. So this is 12,273. So 12,273.15. That's Kelvin. And that will give me my new volume. So I can take my 25, I can multiply that by 523.15, and I can divide that by the 12,273.15. Just making sure I did all the math right. And I end up with 1.06 liters, which I would expect. As our temperature has changed, I would expect that to go down. Okay? So that's that. Questions about that? Okay. Helium balloon with an internal pressure of 1 atmosphere and a volume of 4.5 liters at 20 degrees C is released. What volume will the balloon occupy at an altitude where the pressure is 0.6 atmospheres and the temperature is negative 20 degrees? Okay. So this 1 atmosphere is my pressure, P1. I have a volume of V1 here and a T1 there. I have a P2 that's there and a T2 that's here. And I've been asked about what is V2? So V2 is what I'm looking for. Fine. Well, I have more variables this time. So now I have a P1 V1 over T1 situation equal to P2 V2 over T2. If I'm looking for V2, that is then going to be the space. So V2 is going to be P1 V1 over T1, and then I'll move that T2 to the other side, and the P2. But that's the equation that I need to be using. Isolating my V2 to get it by itself. All right, well, I can set that up. So again, my P1 is 1 atmosphere. So V2 is going to be equal to 1.00 ATM. I'm then going to divide that by the second atmosphere pressure that I'm looking at, just because I have a P1 over P2, so that it makes my life happy if I put the units together. I put that there, the 0.6. My V1, I'm going to put at the end. I'm going to put my T2 here, so 20 degrees C. Oh, look, my temperatures are actually the same. Oh, no, they're not. 20 degrees C here, that's 293.15. And this one is negative 20 degrees C. So I have 273.15 minus 20, which is 253. So looking at what I need to put in, I need my T2, that 253.15 Kelvin. My T1 being the 293.15. And then, of course, I need to put in my volume that I started with, and that was 4.50 liters. Kelvins cancel, atmospheres cancel. That leaves me with an answer that's in units of liters, which makes sense since I'm looking for a volume. I can take 1 times Q53.15 times the 4.50, divide that by the 0.6, and be 293.5. And that gives me V2 is equal to 6. My answers are all 3 6 big, so 4 8. And that's liters. Okay. So gas laws for me are a lot of plug and check. It's a lot of identification of what are my variables. So what are the variables that I'm dealing with? What are the values for those? And then figuring out which equation it is and plugging those in. Okay. Now, one last question. 135 liters of gas in a container at a temperature of 2600 C. If the gas was cooled until the volume decreased to 75 liters, what would the temperature of the gas be? So I'm talking about a volume here. I have a temperature here, and I have a second volume, and I want to know what that second temperature is. So again, volume and temperature. And we're doing this yet again. So V1 over T1 is equal to V2 over T2. Now, since I want to know what the second temperature is, I'm going to have to rearrange this a little bit to get that answer. T2 is going to be equal to V2 times T1 over V1. Okay, so I've rearranged this. I brought the T over to this side, and I brought this expression over to that side, because if I do that, then it gets me T2 on the top rather than on the bottom, which is where I need it. Okay, now my V2 that I have is 75 liters. So 75 liters, I'm looking for T2. My T1 that I'm looking at is 260 C, so 260 gives me 533 Kelvin, and my V1 was 135. Okay, so 75 times the 533.15 divided by 135, and that gives me T2 equals 296. And again, really should only be 2 sig figs because I have a 75. So I should round this to 300, okay, to report it, but I'm going to leave it as a 296. Questions, comments, problems about what I did with that? Okay. And we don't always have a situation where we have an initial set of conditions and then a final set of conditions. So we're not always doing changes that we're talking about. Sometimes what I have is I know that I have a particular pressure, I have a particular volume, I have a particular temperature, and I need to know how many moles of gas there. Okay. Could be that I have a number of moles of gas and I have a temperature that it is. And I need to know what that pressure is going to be so I can make sure that the container that it's in isn't going to explode. Very practical thing for us to be looking at. Now again, our gas constant is actually 0.082057. Okay, that's the big whole thing. We normally round this to 0.0821 just because it makes our life a lot easier if we do that. One of the things that we find is that if I have 1 mole of gas at standard temperature, 0 degrees C, standard pressure, 1 atmosphere, right, then the volume that it occupies is 22.41 liters. Okay? It doesn't matter what that gas is. That is called the standard volume. You'll also see this on your test. It's not labeled well, it's in the same box as Avogadro's number, but that's what that is. Okay? You can use this as a shortcut to be able to find things related to what's the volume going to be in a given set of conditions. It is useful and helpful to be able to do that, but it is not always necessary to use the information in that way. Okay, you can always solve for it in other ways. For changing conditions, if n is constant, you have P1 times V1 over T1 equals P2 V2 over T2. Okay, again, the version given to you on the test has the n included. That way you can look at that. Okay. We can also do density calculations. There is a second lab that goes with the gas laws where you're being asked to calculate what that molar mass is. And the way that we do that is by using the density. Okay. So our molar mass is equal to the density of the gas times R times T divided by P. Okay. Where D is the density of the gas, moles, the mass per volume. So we can use that information to find the molar mass of the gas. This is one of the ways that we find that molar mass that we can use when we're talking about empirical formulas. And we can use this as a molecular formula. Right? So there are a lot of units for R. This is the one that we need when we're talking about gases. Okay? Some of the other things you will get to, if you take 111, you'll get to see a different version of it there, but that's not what we're going to talk about here. Okay? The questions on the ideal gas law, PV equals nRT. If I'm not mistaken, let me just verify because I want to make sure that I'm correct about this. Yeah, the ideal gas law itself is not included. And the reason for that is because it's an extremely common equation that gets used a lot. So that equation itself is on the test. But from here, if you have the n in this, then it's easy to see that, well, okay, it's easy for me to see that P1, that P times V equals the constant times n times T. So hopefully you can solve for that using what you think. All right. Questions, comments, problems so far? Okay. So let's talk about some of the examples we can do with the ideal gas. Because again, this is a little bit different than what we did with our changing conditions. How many moles of gas occupy 98 liters at a pressure of 2.8 atmospheres and a temperature of 292 Kelvin? Okay, fine. I want to know N. It's the number of moles. I have a volume here. I actually can stop labeling them as V1 because that's the volume. This is my pressure, the 2.8 atmospheres. This is my temperature, and of course R is 0.0821 liters times atmospheres over mole times Kelvin. And again, that is available to you on the handouts. I do not expect you to remember it. It's just one of those things that I end up using so often, so I do. So that's that. Now, if I'm looking for N, and my ideal gas law is PV equals nRT, if I want to solve for N is going to be equal to PV over RT. So I can take my pressure, the 2.8 atmospheres. I can take my volume, the 98 liters. I can put my temperature down at the bottom, the 292 Kelvin, and then I can divide by R, which is at 0.0821 liters times atmospheres over mole times Kelvin. And of course, since it's a fraction and the bottom part is underneath, then you can flip that up. So that brings that up there. My atmospheres cancel, my Kelvins cancel, my liters cancel. And leaves you with an answer in moles, which is exactly what I'm looking for. So I'm pretty certain that I've set this up correctly. And as long as my calculator doesn't explode on me, which happens from time to time, then I should be fine. I take my 2.8, I multiply it by 98, I divide that by 292, and I divide that by 0.0821. And that tells me that my N equals 11 points, and it should just be 11 moles. Again, it doesn't matter what that gas is, it's just a gas. It doesn't matter what it is, it will still have that same property. Okay? All right, let's look at another one. 5 moles of O2, 3 moles of N2 are placed into a 30-liter tank at a temperature of 250 C. What will the pressure of the resulting mixture of gases be? Right, okay. I'm going to start at the beginning because I know that 30 liters is a volume. So I know that that's a volume. And I know that this is temperature. I want to know what the pressure is. So then the question becomes, well, what do I do with this moles of O2 and the moles of N2? Well, it wants to know what the pressure of the resulting mixture is. So I can take and sum those two moles to give me the total number of moles. Because again, it doesn't matter what those gases are. I just need to know how much of them there. So my total number of moles, N, is going to be 8 moles. Okay. Awesome. I can do that. I want to know what the pressure is. So pressure is going to be equal to nRT over V. So if I want to solve that, I get my pressure is equal to my N, which is 8.0 moles. I'm going to divide that by that volume that gave me, the 30.0 liters. And that's just to make my train tracks nicer in my head. Doesn't matter where you put it as long as it's on the bottom. I'm going to put my temperature here, the 250 degrees, and that's in C, so I need to convert that. Oops. So 250 plus 274. Sorry, I forgot. 5, 2, 3.1. Now, sometimes when I'm doing work on my own, and trying not to be more clear, I will actually put that calculation in here. If I realize that I haven't converted it yet, I'll put in parentheses 250 plus 273.15. And that'll show me that I need to do that calculation before I do the rest of this. Perfectly fine if you do that. That is perfectly okay. But again, since I've already done that calculation, I'm going to take this out and put in that actual value. And that is Kelvin. And then we take and multiply this by 0.0821 liters times atmospheres over mole times Kelvin. And I really wish it wasn't a 1 and then an L, because I always confuse the two and like L before 1 or 1 and then 1 again. It's kind of obnoxious. I hate it. But that's just an aside. My moles cancel, my Kelvins cancel, my liters cancel. That leaves me with an answer in ATM, which is good because that's what I'm looking for. 8 times 5.3.15 times 0.0821 divided by 30. And that gives me 5.5. And that's ATM. And again, 2 sig figs based on the 8 that I have there. Okay. Yay, that was exciting. Awesome. We can do this. So again, this is really a question of, have I identified everything that is there? And you'll notice that, at least I hope that you notice, that my identification of things is always based on the units they have. So liters goes with my volumes, Kelvin or degrees C goes with my temperature, atmospheres goes with pressures, that kind of thing. So that's what we're looking at in terms of those. Pulling information out. So as I said, 35-liter tank of oxygen is at 315 Kelvin with an internal pressure of 190 atmospheres. How many moles of gas does the tank contain? Well, here's my volume. Here's my temperature. Here's my pressure. I'm looking for N. So if I want N, again, you set this up before, N is equal to PV over RT. I'm going to slide this out just a little bit so I have more space. N is equal to PV over RT. And the pressure that I have here is 35, 190 ATM. Almost put the wrong thing in. My volume is 35 liters. And even R on the bottom, I'm going to skip that for the moment and put my 315 Kelvin down here. And then 0.0821 liters times atmospheres over moles. It's Kelvin. And again, I put the R by itself just to make the units easier, to make sure that I get them where they need to be so I can see it cancel. And that leaves me with an answer in moles, which is awesome because that's what I'm hoping for. So 190 divided by 315 times 35 divided by 0.021. And that gives me, just checking my math, that's all. Yep. 257 is what I come up with. And it's a fairly large pressure, so I'm not overly surprised by that. But you can see that it gave me pause. I wanted to make sure that my math was right and I'd set that up. So, and that's perfectly okay. Questions about that? Okay. I have a 75-liter container, holds 62 moles of gas at a temperature of 2150 C. That's the pressure in atmospheres inside the container. So I'm looking for pressure. I'll take my 2150 plus 273.15 temperature conversion, and that gives me 2423.15 Kelvin. My N is here. That is my temperature. And that is my volume. So I'm looking for pressure. Again, I'm looking for pressure. I'm going to be doing pressure is equal to. Yeah, I didn't write it. I didn't want to do this. nRT over V. nRT over V. My number of moles that I have here is 62 moles. My temperature that I have is at 2423.15 Kelvin. My volume that I'm looking at is 45 liters. And I can multiply by the 0.0821 liters times atmospheres over mole times Kelvin. My liters cancel there, there. My Kelvins cancel there. Answer. Atmospheres, yay, that's awesome. 62 divided by 45 times 2. 5 times 0.021. And that gives me 274. Okay. Awesome. Now, a gas canister can tolerate internal pressures of up to 210 atmospheres. That's a pressure. If a 2-liter container holds 3.5 moles of gas, that's my N, heated to 1350 C, will the container explode? Yes. So 13,500 plus the 273.15 is 13,773.5 Kelvin. Okay. And I want to know if this is going to explode. So I'm looking to see what that actual pressure is, because they can hold up to 210, but I need to know if the pressure is going to be bigger than that, right? So I need to solve for pressure yet again. That means that I need to set this up with my number of moles, which I was given as 3.5 moles. I'm going to divide that by the volume that this container is. It's a 2-liter container. I have my temperature, which is 13,773.15 Kelvin. And of course my R, which is 0.0821 liters times atmospheres over mole times Kelvin. Kelvins canceled there, moles canceled there, liters canceled there, and all these atmospheres. And I'm pretty sure that that number is going to be bigger than 210, which means it will explode. But these aren't always as exaggerated as this. So 3.5 times 13,773.15 times 0.021 divided by 2. And that gives me 1978 ATM. So yes, that will explode because again, that pressure is higher than the 210 that it can handle, right? Now, like I said, this is a very exaggerated example because our temperature is extremely high. But we may need to solve for something like this to see if that pressure is going to be too large. This is actually something I do in when I'm considering leaving soda in my car, because I know how to calculate what temperature will be okay and what temperature won't be okay for my sodas to explode. So I can guesstimate based on what the temperature is expected to be, whether I think it's going to be safe or not. Do I always get it right? No, because their accuracy on what they guess the temperature is going to be is not always right. So sometimes it goes wrong and it does explode, but that's because I was silly enough to leave it in the car again. Okay. So questions, comments, problems on any of our ideal gas equation example. Okay. Now, sample calculation using the density of gas. So what is the density of oxygen gas at 5 atmospheres and 27 degrees C? Now we know that density is equal to the pressure times the molar mass divided by R divided by T. That's how we can get that. The density being mass over volume. So that's what we're looking at. So I know that my R is 0.0821 liters atmospheres per mole Kelvin. My temperature is 27 plus the 273.15, which gives it 300.15 Kelvin. Pressure is 5 atmospheres. And the molar mass for oxygen gas is approximately 32. I use 32 as my calculation here. So I take my pressure, 5 atmospheres, divide that by my temperature, 300.15, multiply that by the molar mass, 32 grams per mole, and then divide by R, which is 0.0821 liters atmospheres per mole Kelvin, and that gives me a density of 6.5 grams per liter. So I can calculate the density of gas, given certain conditions, certain pieces of information. Now I also can see that as a certain reaction occurs, producing an oxide of nitrogen gas. The gas has a mass of 1.211 grams and occupies a volume of 677 milliliters. The temperature in the laboratory is 23 degrees C and the air pressure is 0.978 atmospheres. Calculate the molar mass of the gas. And again, one of the calculations that's done in the laboratory is to calculate the molar mass of the gas. So this is an example of how we would do that. So we have our mass, we have our volume, we have our temperature, pressure, and R. So N is going to be equal to the P, which is 0.987, multiplied by the volume, which is 0.677 liters, divided by that R, 0.0821 liters atmospheres per mole Kelvin, and the temperature, 296. So N is equal to 0.0275 moles. I know the number of moles. Since the mass is 1.211 grams, the molecular weight is then 1.211 grams divided by that 0.0275 moles, which gives me 44 grams per mole. And so if I know it's a nitrogen oxide, I can calculate what the NO would be and see that that's probably not right. And I can calculate what the NO2 is going to be and see if that's right. And we keep doing those iterations until we figure out what that is. Now, that's an ugly way to do it. If we have an empirical formula, that helps, but that's not always something that we have. Okay? We may just know that it's nitrogen and oxygen, and may have to go about the guesswork of how I get to 44 from those two masses. Okay? So that's how we would find the molar mass of that gas, to solve for the number of moles and then look at the mass that we have for that and divide it by the number. Questions, comments, problems? Okay. So stoichiometry roadmap. We've seen this a bunch of times, right? And this is just a different view of what we've talked about before. So I have done the mass to moles to moles to mass, which is the directly horizontal portion of this, right? That I've calculated a number of times. I can also calculate from the number of moles the number of particles. So that's the bottom portion of this. Now we're able to look at the volume of a gas at STP to calculate the number of moles. I can also use PV equals NRT to find the number of moles from volume or from pressure or from any number of those things. So I can get from information about that gas to the number of moles of that gas, and then use that to get over here to moles of something else in that equation, and then get back to the volume or the pressure or the temperature or the mass or the number of particles. All of those are valid calculations. And so that's just another piece of that stoichiometry map that's in your exam handouts. Okay? Isolation of this part of it, so it's not as big and ugly as the other. Questions about that? So, an example calculation of gas stoichiometry. Remember that, PV equals NRT. So let us consider 3S plus 3O2 plus 2H2O goes to 2H2SO4. So I can take sulfur, add some oxygen gas to it, add some liquid water, and make sulfuric acid. I want to know what volume in O2 in liters at 22 degrees C and 745 millimeters of mercury is required to produce 1 ton of H2SO4. Okay, it's a ton. So the first thing I need to do is get that to a unit that makes sense with other things that I work with. So I need to convert that ton to moles. I do that by converting the ton to grams. So 1 ton is 907.907,185 grams. So that gives me 907,185 grams of H2SO4. I can convert the grams of H2SO4 to moles of H2SO4 by dividing by the molecular weight of H2SO4. It gives me 9891.873 moles of H2SO4 that I need to have from this. Now, that's moles of H2SO4 that I need to produce, so I need to know how many moles of O2 are required to do that. So there are 3 moles of O2 required for every 2 moles of H2SO4 that are produced. So doing that conversion tells me how many moles of O2 are required to do this. So now that I know number of moles, I know that I can use the number of moles to plug that in. For N, I can then figure out what my temperature is in Kelvin. Okay, so I can convert that. And then I can find the pressure that I have, that I know that. And I know R, so I can figure out what that volume is that I will need. So I do my pressure conversion. That's that 22 to 273 gives me 295.15 Kelvin. I convert my pressure in millimeters of mercury to a ATM. Remember that 1 ATM is 760 millimeters of mercury. So I take my 745, I divide that by 760, and that gives me 0.980 and change ATM. So now I have P, N, and T, and I know R, so I can solve for V. So volume is equal to nRT over P. I plug in all of my happy values in here that I just solved for, and that gives me 366786.3 liters of O2. 3 sig figs, because I looked at 1 ton, so I should be reporting that as 3.67 times 10 to the 5th liters of O2. Okay. And again, this is a practical consideration. If I'm working in a laboratory where we have been asked to produce 1 ton of H2SO4 for a customer, I need to make sure that I have enough oxygen around to make that happen. So this is a way for me to do that calculation to make sure that I have enough oxygen. And of course, this needs to take into account the percent yield to make sure that we've got an actual enough of it. But this is a very good estimate to where we need to start. I will definitely need more. Okay, so questions, comments, problems about using that in combination with the stoichiometry that we've been doing. Okay. Now, what's that other thing we need to do? Well, Dalton's law of partial pressure. So the partial pressure ideal gas pressure that is measured in the atmosphere comes from a mixture of gases. N2, O2, HE, NE, CO2, all of those things are part of that mix. The contribution from each gas can be calculated using a modification of the ideal gas law. So the pressure of each gas is due to the number of moles of that gas also being considered at that temperature and at that volume. So what that means is that the pressure of each gas can be calculated from that. The pressure for each gas, all of those pressures added together, is the total pressure. Okay. So total pressure can come from the sum of the partial pressure. Now the pressure of one gas can be written as the pressure of A over the pressure total. That's actually equal to the number of moles of A over the total number of moles. And that is called chi. So that's a mole fraction. We talked about this when we talked about concentrations, when we talked about solution chemistry. So we also use that here. It's a mole fraction. So the number of moles of this component that I'm looking at compared to the total number of moles, that's a ratio that tells me how much of that pressure is due to that one material. And so if I know the total pressure and I know the mole fraction, then I can calculate the pressure from that particular component. Okay. I can also calculate a chi based on the partial pressure of one gas and the total pressure. That is possible. There are a number of ways that we can exploit this, but it is a very useful relationship for us to know when we're trying to talk about one part of that total. Okay. Questions about that? So some examples that deal with some of this. So these are examples taken directly from the textbook. So this is question 5.66. The sample of air contains only nitrogen and oxygen gases with partial pressures of 0.8 atmospheres and 0.2 atmospheres respectively. Calculate the total pressure and the mole fraction of the gases. Okay. So I have nitrogen, that's an N2. I have oxygen, he's an O2. Pressure of the nitrogen is 0.80 atm. My oxygen is 0.2 atm. I wanted to calculate the total pressure, so that's 1 atm. I add those two together to get my total pressure. And of course, my mole fraction, because my total is 1, my N2 mole fraction, chi N2, is equal to the 0.80 atmospheres over the 1 atmosphere. So that's 0.80, and that's a fraction. My chi for the O2 is equal to 0.20 atm over 1 atm, 0.20. Now, are the examples that you get always that simple to calculate? No, not always, but I hope that that is a better representation of what exactly needs to get done. That was the idea, is to use some simple mathematics to represent our idea. Okay. When we talk about 5.74, a sample of ammonia, NH3, is completely decomposed to nitrogen and hydrogen gases, overheated to iron gold, if the total pressure is 866 millimeters of mercury. Calculate the partial pressures of N2 and H2. Okay. So I have all of this NH3. It decomposes to N2 plus 3H2. Okay, that's my balanced equation. So I know that my pressure from the H2 is equal to the mole fraction of the H2 times the total pressure. And the partial pressure of the N2 is equal to the mole fraction of N2 over the total pressure. Right, now I know that total pressure. That PT was given to me as 866 millimeters of mercury, right? But I can think about this in terms of the moles of N2 over the total number of moles, right? Now, my moles of N2 is 1. That's based on this. My moles of H2 is 3. So my total number of moles is 4. So my X from my chi for my N2 is equal to 1 over 4. And my chi for H2 is equal to 3 over 4. So I can use that balanced equation to find my mole fractions. And then I can take that 1/4 of the 866 millimeters, right? And 3/4 of the 860, and that's a 866 millimeters of mercury. And that'll give me the partial pressure from each component. If I wanted to do that, I can do that. We can do that from the ratios that are given to us in this case. And that's because of what we're looking at. Okay, so questions from that? Okay. A healthy adult exhales about 5.0 times 10 to the second milliliters of a gaseous mixture with each. Calculate the number of molecules present in this volume at 37 degrees C and 1.1 atmosphere. List the major components of the gaseous mixture. Right. Okay. Looking at this, the things that occur in my head, I need to do a conversion from temperature in degrees C to Kelvin. I need to convert from my volume to liters. I need to calculate the number of moles, and then I can calculate the number of particles. Okay. So let's do our temperature conversion. That's 37 plus 273.5. And that's 310.15 Kelvin. I know that I have 5.0 times 10 to the 2 milliliters. I'm going to convert that to liters. I know that there are 1,000 milliliters in 1 liter. So 5.72 divided by the 1,000 gives me 0.5 liters that we're talking about. Based on that, I know that I have PV equals nRT. I have a pressure of 1.1 atm. I'm looking at the volume of 0.5 liters. I want to calculate the number of moles. I know what R is. That's 0.0821 liters atmospheres per mole Kelvin. And of course, that temperature, which is not going to fit right there, is my 310.5 Kelvin. So I can rearrange all of that happy stuff. I'm giving 1.11 atm times 0.5 liters divided by the 0.0821 liters times atmospheres over mole Kelvin, and of course I also need to pull over that 310.1 Kelvin. So I can cancel my kelvins, I can cancel my liters, I can cancel my atmospheres. I'm using with an answer of moles, which is of course what I'm looking for, and this is just 1 over that 310. Let's hope everybody gets filled in and everybody's happy. So 1.1 times that 0.5 divided by 0.0821 divide 310 from 5. And that gives me 0.0216. And it should actually be 0.022 because it's two sig figs based on the number of figs I have in my Amazon. And that's moles. Now that I know the number of moles, I can take that calculation and I can multiply that by Avogadro's number. So 0.022 moles times 6.022 times 10 to the 23rd particles per mole. Moles cancel. So I can multiply that by 6.022 on the third. And that gives me 1.30. And of course, should be two things, so 1.3 times 10 to the 22 particles. Okay. So that's how many particles are in. That's awesome. Now, the second part of this question is a little more esoteric. It says list the major components of the gaseous mixture. I just want to know that you have some idea of what kinds of things would come out when we breathe. We have CO2, that's the major component. We do have some O2 that's left. There is always some other components like N2, HE, any of the other gases that are typically present in the air will still also be part of that explanation. Okay. Does it matter that you give them all? No, of course not. I just want to know some of them. Okay. So questions, comments, problems about that? Okay. And that is everything that I have to talk about in terms of gases. Now, one of the other things that I agreed to do today was to talk over any questions that you guys had in relationship to prep for the test. So, does anybody have anything they want to talk about in terms of looking at the exam practice? Or any other questions, comments, problems at this point?
Man, can you hear me?
Yes.
Hi. So the sheet that you posted on the announcement yesterday, the day before, we are allowed to add that to reference package that we're allowed to use on the exam.
So, are you allowed to add it? Yeah, okay, you can. It's present on the test already, but if you want to add that, yes, you can.
I see. Okay. So it'll already be available on the exam.
It should be,
Okay.
yes. But if you'd rather have a printed copy, I am fine with that.
Okay.
Yeah, I don't expect you to order it. Anything else? So again, please remember that the exam is Monday morning, 8 to 10. As long as you start before 10, that should be fine. And turn in your scratch work so that I can get that done when I'm doing it right. Again, it's more of an issue if the answer is not correct, so that I can see if you had the right path to get to that answer. So that's more important than anything else. I think that's it. I think the only other thing I wanted to talk about, the stoichiometry is not yet due. It's going to be due fairly soon. That post lab for stoichiometry, there is a sheet of paper that goes with it that you were supposed to have filled out before you did the post lab. Please make sure you turn those in because I don't see that any of them have been turned in yet, and that's fine, they're not due yet. I just want to make sure that you guys turn those in because again, partial credit can be given for that if there were mistakes made in that calculation. Okay. And I will be going back into Alex probably this weekend because there is some hand grading that needs to get done on those post labs so that you guys get the points that you deserve. Okay. Now, if there's anything that you have noticed while you guys were working on Alex, you think is weird or strange or didn't give you the grade that you thought that you deserved, make sure you bring that to my attention because I know that there are some things where like it does weird things with sig figs. So I'm trying to catch all of that. But if you've noticed it, make sure you let me know so that way I make sure it gets taken. Okay. Well, I'll be hanging until 10. So if you've got questions, let me know.
Because I know this is, if I'm understanding this correctly, this lecture is for exam 3.
That's correct.
Okay. So, just kind of for my own sake of ease, I was wondering, um, because I know there's some practice problems, I know there's some stuff like that. Do you think it might be a good idea to like go back through the lecture when I have a bit more time and kind of just write down like, hey, I don't understand this from this slide, so on and so forth?
That if that's going to be helpful to you, I know for me that was helpful as a student was to go through. Okay, I don't understand what this says. And make sure that I get those things cleared up. However you want to handle that, whether that's looking at it yourself or talking to me about it, that's perfectly fine.
Gotcha.
If you want to do that, that's great.
Okay, and another thing, because I know you and I, we worked a lot. I believe it was yesterday,
Yeah.
on a lot of work that I just wasn't quite understanding. I was going back through those 3 stoichiometry questions that we had
Yes.
left, so I could do those on my
Right.
own. Um, and I was just essentially I was just getting it wrong. Like
Okay.
some for the math and something else. So I took a screenshot of my scratch. I took a picture of my scratch work. I took a image of the problem. Would you be okay if I sent that to you and you can kind of
Oh yeah.
help me work through that? Okay, I appreciate
Yes.
that. Thank you.
And and if that's not something that we can deal with over email, I will contact you and let you know.
Alrighty.
Hi, can you hear me?
Yes.
I wanted to ask if anything from exam 1 is going to be on exam 2 or if it's just purely these last I think it was 7 through 10 chapters.
So it's very difficult for me to say no. There's nothing from exam 1. So there's no question that's meant to be in a review. All right, that's true. But what happens is that the material from exam 1 will show up in what we're talking about for this. So there is still stuff that's from exam 1 that's on this test. So, like I said, there are no questions that are directly meant to be a review. There's nothing like that. But there are going to be things from exam 1 that are. Yes.
All right, I got it. Thank you.
Sure, no problem.
If I have questions over the weekend, is that something that I can email you, or would you prefer us not to contact you over the weekend?
You can contact me over the weekend. It's easiest if you email me through Outlook email because I get a notification about that one, so I see it faster. I try and check my email the weekend before a test 5 or 6 times every day, but I can't guarantee when that's going to be, so it
Yeah.
may be a weird time. So, but yes, I will definitely be checking. That's perfectly fine.
Okay, so through not through DTL, through Outlook.
If you do it through Outlook, I get a notification. That way I know it's there and I can deal with it as soon as it comes through. Yes.
Okay. I think that is my plan going forward this weekend is to finish up the review. You have a draft of questions so far, so I plan on doing that pretty soon.
Sure. and that's perfectly fine. I'm perfectly okay with that.
Thank you so much.
You're welcome. Thanks.
I'm not sure if you've gotten the email yet.
I just saw it.
Yeah. Because I was the reason why I was a bit confused about it is because I was basing how I was doing those calculations, which may very well be wrong. I know I still feel like I did it right, but obviously, something was messed up. Um and but I was following the kind of outline of how we did um the other problems. Like I was writing it all down as we did it.
Yep.
So I'm not quite sure where I went wrong in regards to it.
And that is okay. Give me 2 seconds. See, I see the question. There, there, scratch mark. If I scroll down, I can see the scratch mark too.
I had it's another photo that was
Yeah,
uploaded.
no, I just didn't see it the first time. That's all. I was
Oh,
like,
gotcha.
wait.
Oh, gotcha.
Okay. Something. I think the mass on NH3 is incorrect.
The
So-
mass on NH3?
Yeah, the molecular weight. I see you have written down 15.014.
No, yeah, that does look right. That does look wrong.
It should be approximately 17, and that's why I'm questioning that, because the other one I think looks okay, but I'm not sure. But
Yeah,
Suspect-
17 point. Yeah, my math on NH3 was wrong.
and that's probably
17.02995.
that's probably that error right there.
See if I can't go in and find where I did the math problem on the calculator history.
Yeah, I have a tendency to clear my calculator history. It's not helpful.
Or I can just redo it real quick. So we've got 4.98 multiplied by 1 multiplied by 1 multiplied by 149.084732 divided by 17.02995 multiplied by 3 multiplied by 1. I get a I no, yeah, that is the right answer. So it was an error of, I think that's for measurements called AMU.
Yes. Yeah.
Um,
So it's actually grams per mole when we talk about the moles, but it's AMU if we're talking about one molecule. But yeah, I think that looks like you only added the one hydrogen and not all three of them.
yeah, that is what happened. Because I redid my railroad
Yeah.
with the correct information, and I got that 14.5.
Yeah.
Gotcha. Okay. Um, gonna admit, I kind of had a similar problem with today's lecture, but that is also probably due. I think I know why. Like not with like the math, but kind of not really getting it. So I'm running on fumes. I probably got like 3 hours of sleep, but also
That's
B,
good.
I was trying to do it on my phone. You might have saw me like leave, then immediately come back in.
Yeah.
and just the audio on that was awful.
I'm sorry. Well,
No, it's not on your end. Just my phone was like, no, I'm not going to turn up the volume. It was just like, no, I'm going to be silent as the grave, and you're going to suffer. And that's how it's going to be. So that's why I was saying, what I'll probably do is I've got to go help a friend with an AC unit. But once I'm done with that, I'm going to re-watch the recording of the lecture, and I'll
Yeah.
write down, hey, like, here's what I understand, here's what I don't understand, because, well, I understand what I understood from it, is I understood, like, hey, here are the different kind of variables that are involved with measuring and calculating gas and pressure and the volume of gas and so on and so forth. But when it came to applying those in formula, that seems to be my big problem. It's like I can get what we're supposed to put into this, but I don't know how this is supposed to be organized, this being the formula. That always seems to murder me.
Well, and again, so PV equals RT does not appear in the exam habits, but the P1 V1 over T1 N1 does. And in my opinion, you can get from that. So one T1 is equal to the same kind of thing for P2, but that's equal to a constant. And so if you then do P1 V1 equals nRT, that's the ideal gas law.
Okay, I'm not going to even try to say that makes a lick of sense to me right now. That's part of the reason why I'm going to rewatch the lecture, because
Okay.
that way I can see where you were explaining it and actually hear you.
Sure.
If I get it, bravo, kudos. If I don't get it, I'll let you know, and we can
And that is great.
work out a
Yep.
time to try and fix that problem.
We can. Absolutely.
I'm not normally so, like, proactive, I guess I would say, in regards to this, because I guess kind of my thing is I'm generally, this is kind of how I've always been, is generally I can read information, remember it, not have to study, pass with high B's, low A's. That's almost how I've always been. And this class is not that. This is not.
No, it really isn't. Which is
This
why I liked it.
it's bullying me. But I think it's a healthy kind. It's like you gotta learn, and if this class has to beat my skull into the ground a little bit for me to learn my lesson,
I think a lot of people who end up going to college do okay in high school without really having to do anything. And this is where a lot of people learn that sometimes you got to do some work to do things. And that can be a hard transition.
Yeah. But no, not just trying to, like, chew the fat or anything. I guess I was just kind of explaining things. But no,
That's fine.
definitely that was just a grams per mole atomic mass unit error. So what I'm gonna do is I'm gonna go retry those 3.
Okay.
See if I can't try and get them all done before 10.
Okay.
And if there is any issues, I'll stay in and just kind of unmute myself and let you know. But otherwise, if I can get this right and I don't have to speak to you again, wish you a lovely day. If not, I will be speaking shortly.
Okay. I'm gonna exit the meeting, come right back in. That way I can get this processing so I can post it.
Gotcha. All right, no problem.
Sure. I'll talk to you soon.
Talk to you soon.